Right. This is lecture one, about chapter one for the introduction to statistics. We're going to be going over some terminology and a little bit of mathematical operations, but this should be a fairly easy lecture. If you have not read the first chapter, be sure to do so because there's still a lot of important information in there. All right, what are statistics? Well, statistics are a set of mathematical procedures for organizing, summarizing, and interpreting information. And we use stats in order to help determine whether there are differences among groups of organisms, and if there are, whether or not these differences are likely trivial, right? So perhaps due to chance, right? Or are they significant? Are they due to something that might be interesting and worth studying? And so psychology is the scientific study of human behavior. And because psychology is a science, then research and statistics are fundamental components. And as a consequence, we use stats in all sorts of fields of psychology or all sorts of subdisciplines. For example, people that are interested in counseling psych might be interested in this notion of whether or not one therapy works better than, say, another therapy in order to reduce anxiety. And that can be tested, right? The effects of those different therapies can be tested. There can be some sort of quantitative output or outcome of these therapies, and a counseling psychologist can determine which sort of procedure or process is superior. In social psychology, they might ask, does a job applicant's sex or gender impact their chances of being hired? Right? Another thing that could be quantified as some sort of output. Statistical testing can be used to determine whether or not there's a difference between multiple groups. Some others, like cognition, right? How can we improve decision-making accuracy? Or developmental psychologists might be interested in determining what the average age is of the onset of puberty. There's even a field called industrial organizational psychology, right? Or consumer psychology. And those sort of researchers might be interested in asking what product qualities are most desired by a target consumer. So the point is, if we can quantify something, right, that is, we can extract some sort of numerical values among the variables of interest, then we can compare those numbers to mathematically determine if they're different. And so, well, there's a number of reasons why you should care. I mean, first of all, your psychology majors, right? So hopefully your sort of subjects within your major are something interesting to you, but you can also make an argument this is important as a consumer. Whether you graduate from college and work in a large corporation or some sort of small family-owned business, or you start your own business, or maybe you work as a teacher or work for an NGO or a politician or something, it's very likely that you'll deal with data in some way or another. So let's go through a handful of terms here that are important for you to understand. The first thing is variable. Variable is any characteristic or condition that can take on different values. So variables can vary naturally, right, from person to person, right? Typically, we're all different heights, weights, gender, IQ. We might have different scores on an exam. Variables can also be manipulated by the experimenter, right? So, I don't know, a couple of examples here. Maybe I'm interested in studying the effects of room temperature on scores on an exam, all right? So I can manipulate room temperature among two different groups. I could have one group take the exam in a room that's incredibly warm, right? Maybe I've got the temperature bumped up to like 80-something degrees, and they take the test, and I have an output there, right? Their scores on an exam. Then I can have another group that takes the test in a more comfortable room, say, 65 degrees or something like that. And I can repeat the procedure with this different group, and I can do some sort of statistical analyses to determine whether or not these two groups are different. So what I'm manipulating here is the room temperature, right? There are a number of different ways we can do this, and we'll discuss these sort of possibilities throughout the semester. A variable can also be constant if it has any characteristic that can't take on different values, right? So let's say you all take this exam, and I add 5 points to everybody's score. I'm going to change the overall group mean as long as I do it for everybody, right? As long as I keep it constant, uh, then uh, then it has a characteristic that can't take on different values. Now, data are measurements or observations obtained in a research study. And when we talk about data, we're talking about measurements or observations of study participants or study subjects. So for most of the examples in this course, our study subjects will be human beings, they'll be people. But these same techniques that we're learning in this class about data analysis and statistics, they can be applied to many other types of subjects like trees or animals or virtually anything that can have some measurable output. All right. So a couple of other terms here, the idea of population and sample. And this is very important because this will be sort of a recurring two terms that we'll talk a lot about in this class for the semester. So in research science, we study samples of people, right? Samples of people, right? A subset of the population, in hopes of being able to make inferences about the larger population, right? The complete set of individuals in an interest of interest in our study. And what's a population? Well, population can be all human beings on Earth, right? We might be interested in making some sort of inference about every living person, but we can define it to whatever way makes sense. Maybe we're interested in all women, or maybe we're interested in all adolescents in the United States, or dog owners, or employees of the university. We can set sort of the parameters for that, or sort of the we can define that population as we see fit. Typically in psychology or any of the social sciences, we're trying to make inferences about all humans in a sense, right? We're trying to run a study of a smaller group of people, in this case a sample, and make inferences about how the data from that sample might reflect our larger population. So a sample, right? It's a group that consists of some but not all members of the population, and it's intended to represent a population in a research study. So imagine, I have a garbage can filled with thousands of different marbles of different colors that you see there in the middle, and there are different numbers of each color of marble, right? So to get a good idea of what proportion of marbles are each color, without sort of having to count sort of several thousand of these marbles, I could take a sample, right? I could randomly reach in and grab a handful of marbles, right? Maybe I can grab 25 marbles, and if I count them up, well, maybe that's the same. I have the same ratio of blue and green and red and white marbles that is representative if I were to count all several thousand of these marbles. If I take more marbles, if I take 100 or if I take 200, well, then I've got a better chance. If I then count that sample, say of 200 marbles, I have a better chance by taking more marbles of having a actual representation of what the different proportion of colored marbles are in my big garbage can of thousands of marbles. So typically, though, statistics is almost always dealing with samples rather than large populations, right? And the reason being is because it's much easier to take a subset of people, right? 25, 30, even 100 people, run an experiment with those people, than it is to take the entire population that you might be interested in, right? Like, obviously, it's impossible to do something where you measure every single human being alive or every single sort of adult human being that might be able to participate in an experiment or survey. It's quite easy to take a subset of those people, and then hopefully you're able to make inferences about the larger population. One thing I like to think about in regards to this is this idea of how making pasta, right, is like generalizing from a sample to a population. And sort of the idea here is think about how you make pasta from start to finish, right? One sort of question is, how might you decide when it's done? Now, typically when I ask this to a class of students, I get Well, I tend to get sort of one common answer. Most people are surprised by the second, which is the way I determine whether or not pasta is done. But one thing is you might, time it for how long it's supposed to boil in the pot. Like, let's say it's supposed to boil for 9 minutes, depending upon the sort of firmness you want your pasta. You might take out a few strands, right, and taste them, see if they're done. And if those few strands are done, right, then the rest is probably done. My way of doing it is actually taking a few strands and throwing them at the wall, because the rule of thumb here is if they stick, then they're actually done. The second is my favorite because clearly you don't want to throw all of the pasta at the wall, right? It's sort of besides the point, right? So what you do is you provide a random sample of the pasta, right, by just taking a handful of strands. And I assume that the strands I've selected is the same as the rest of the pasta in important ways, right? That it's done. And so the sample should do a good job, right? These few strands of pasta should ideally do a very good job of explaining the doneness, if you will, about the rest of my pasta, right? I mean, there's we can discuss the important similarities, right, such as length of time of water and closeness to the heat of the stove and so on and so forth. But the sort of take-home message here is like, you can pull a few strands out, throw them at the wall. If they stick, then you can make assumptions about the rest of your pasta, and that's very much what it's like to take a sample, right, of people and do a study and make inferences about the greater population. All right, let me take a sip of coffee here. These two terms here, parameter and statistic, also relate to this idea of population and sample. And it is what we call it's a descriptor term. So let me just say this: a parameter, right? A parameter is a descriptive value, right? Typically something numeric, but it could be nominal. That describes a population, whereas a statistic is a descriptive value that describes a sample. So if we used our class of students as a sample, and maybe I ask every person, how many movies did you watch over the break? We can then calculate the average for the class, right? And that average, right, that value, right, that mean would be called a statistic. Now, what would we have to do to calculate the parameter, right? Well, we'd have to ask every single person in the university, or every single student in the university, how many movies did you watch over the break? And then we could take a mean of that, right? We could compute the mean of that. And that would be a parameter, right? So a statistic, a value like a measure of central tendency or variance that we'll learn about later. For a sample is something that we would call a statistic. But if we could do that for the entire population, right? If we could get a mean or some measure of variability for the entire population, we would call that a parameter. So there's a difference between a statistic is a value, right, that represents either a sample or a population. Descriptive statistics, however, is what we do, right? It's it is the tests that we run, right, in order to analyze the data, right? It's the procedures we use to summarize, organize, and simplify the data. And descriptive statistics, it's a term that is, I think, self-defining, where we use descriptive statistics to describe the basic features of the data in our study. They provide important summaries about the sample and the measures. So what are we talking about here? Something like computing a mean or an average is a simple descriptive statistic, right? If I were to say the mean number of movies we watched over break was 5, then that's a very simple, informative way of relaying information. And additionally, we can descriptive statistics can be easily organized into things like graphs, right? Figures, that chart differences over time, for example, or differences between groups. Or we can organize them as tables, right, which is essentially doing the same thing. And these sort of figures and tables, they can quickly convey a lot of information about the data. And so there are different sort of additional terms that you need to know as they relate to the types of statistics. One thing is inferential statistics. So these are the techniques that allow us to use sample data to make general conclusions about the population. And so with inferential statistics, we're trying to reach conclusions that extend beyond the immediate data alone. So for instance, we use inferential statistics to try to infer from the sample data what the population might think, or we use inferential statistics to make judgments of the probability that observed difference between groups is something that's dependable. Or alternatively, it might be something that we just happen to stumble upon by chance in the study, right? By randomness. So we use inferential statistics to make inferences from our data, to make more general conclusions, right? We use descriptive statistics simply to describe what's going on in our data, right? So to put this more simply, inferential statistics, they're the statistical tests we run, right? And descriptive statistics can be thought about as the output. And then there's something called sampling error, right? This is the discrepancy that exists between a sample statistic and the corresponding population parameter. So a sample can't be expected to provide a perfectly accurate picture of the whole population, right? Because you're not measuring the entire population. So there's usually some sort of discrepancy between the sample statistic and the corresponding population parameter. This is something that we call sampling error. So let's say on average, people in the class watch 5 movies over break. Well, this sample statistic might give us a good idea about what the parameter would be for all the students at the university. But we would have to expect that there's going to be some sort of sampling error, right? So maybe the average for all of the students in the university might be a little bit higher, might be a little bit lower, and that's what sampling error describes. So one way that you might have had some experience with this before you started taking this class is whenever it's time for an election, as we get closer to the election, there's all this polling data, right? And you might see at the bottom of every poll, this poll is accurate between plus and minus 3%, right? And that's an example of sampling error, right? Because what happens in polling? Do they poll every single person that's eligible to vote in an election to see which percentage might favor one candidate or the other, or one issue or the other? No, of course not. It's impossible. Typically, they survey anywhere from 100 to 1,000 people at random. And because they know that they're not measuring every single person in the population, they have to assume that they might be off by a little bit, right? And they can actually calculate how much they think they may possibly be off by, right? They can calculate that window. And in polling, they call this the margin of error, right? So maybe 40% of people approve or say they're going to vote for candidate A, and 60% say they're going to vote for candidate B, plus or minus, say 3%, right? That plus or minus 3%, that's the sampling error. All right, so now is typically the time you ask if you have any questions. We've defined a handful of terms, so here I also want to mention that there's data that I like to use throughout the course of the semester that I collect from you guys. It's benign data, right? I ask you questions like, how stressed out do you think you'll be this summer? What year are you during your undergraduate right now? What's your GPA? What's your eye color? Things like this. There's a handful of questions you can find on the course website, and there should be a due date posted up there for when you need to answer those by. If I get at least 80% of the class participates in this survey, I will add 2 points, right? 2 points to everybody's final exam score, right? So if 80% of you guys participate in this survey, which should take you no more than 5 to 7 minutes, then you will get 2 points. Everybody will get 2 points on their final exam. I should also note that, and I think I probably said this in the last video, that quiz 1 is already up, and if I recall correctly, that's about 5 questions that relate to the syllabus. And that also has a fairly quick due date, which is different from most of our quizzes. Typically, your quizzes, you'll have a 24-hour window for which you'll have to take them. This one, I think I'm giving you several days, probably up to Friday or maybe the weekend. I apologize, I don't remember off the top of my head, but you can look in the syllabus to find that out. So be sure that you participate in this survey and that you get quiz 1 done as quickly as possible before the due date, so that you get your points. And in regards to the survey, everything is anonymous, so I won't know what your answers are. But again, I'm not asking you anything that should be sort of embarrassing. So After you are finished with this course, right, you're going to take a course called Research Methods, right? And in that Research Methods class, you're going to apply everything that you have learned in this class, right? All the statistical analysis you've done, you're going to be applying them to real life psychology problems. Depending on sort of who you take the class with, you might find yourself even giving the assignment for a final of getting out there with a group of your peers and running your own experiment, which is always good fun. And you'll then have to collect the data and then analyze the data using these statistical methodologies. That being said, even though it's its own class, there are a few terms that the book covers that I think are useful for us to cover in this first class, that while you'll learn more about them in the next class, much greater detail, I think you need to have sort of a basic understanding, a basic fundamental understanding of some of these terms and research methods in order to be successful in this class. And so I want to talk about a couple of different ways in which experiments are performed, or really ways in which some of these methodologies are thought about at a sort of a high level, not necessarily in the weeds. And so one of those types of analyses that you might find in a psychology experiment is something that's called a correlation, right? And in a correlation, what we're doing is we have two variables, and we observe those variables, and then try to determine through statistical testing whether or not those variables are related, right? So we're asking, again, in a correlation, are two variables related in some way? So here's a couple of examples, right? Maybe there's a correlation, right? There's a relationship between the amount of time you spend studying and your score on the exam, right? And if we were to plot that for every single participant in the class, right? Okay, how many hours did you spend studying? Okay, so that's a data point. And then I look at your score on the exam, and that's another data point. And typically you might expect to find a relationship between these two variables, right? If you spend more time studying, then it's likely, especially if you're studying effectively, it's likely that you'll do well on the exam. But conversely, if you don't spend a lot of time studying on the exam for studying, then you probably won't do very well. We might find a correlation between a person's age and maybe the number of hours that they spend on social media like Instagram, right? So if you're my age, I don't even have an Instagram account, so and I'm definitely older than you guys. I would be a zero, right? I spend a zero amount of time on Instagram, right? But you guys that are younger, right? Instagram is part of your sort of youth culture, right? It's what the kids are into today. And we might find that younger people might spend more time on social media networks like that. We're going to discuss the mathematics behind correlations at the end of the semester, I think chapter 15. But the one thing I want to point out is we're not looking to see if being high on one variable causes you to be high or low on the other variable, but rather we're just looking to see if those two variables are related. Now, they may or may not be causally related. We don't know about that, but we're just, because correlations won't tell us that, right? You've probably heard correlation does not equal causation. That's because typically we're just observing variables as they occur in an environment and then seeing if there's a relation. We're not manipulating them in any way so that we can show causality. One of my favorite sort of examples over here is you see in the upper part of the figure there, upper part of the slide, this idea that there's a relationship between a correlation between ice cream sales and shark attacks, right? And you think, well, there's no causality necessarily that can be applied here, right? What would that mean? That would be, if we were to say there's causality, we would be essentially saying that eating more ice cream increases your likelihood of being attacked by a shark, right? Which is a bit silly. But why would these two variables seemingly be related? Well, likely has to do with temperature, right? So as we get into the summer months, it's warmer, people eat more ice cream, right? But also as we get into the summer months, depending on where you live, more people are probably going to go to large bodies of water where there might be the presence of sharks, and as a consequence, more people are in the water during the summer, then it increases their likelihood of getting attacked by a shark. But to say that these two relationships have some sort of cause-effect right? Or these two variables have some sort of cause-effect relationship, is absolutely, utterly silly, right? It doesn't. But nevertheless, if we were to perform some sort of statistical analyses on this, we would see that there's a very strong relationship between the increase or between ice cream sales and the prevalence of shark attacks. But they're not. There's no causality here that can be inferred. That's the important sort of point. This is one of my favorites because maybe because I'm a big fan of red wine. But undoubtedly, you've probably heard in the media that drinking a glass of red wine is associated with a bunch of health effects, right? We think, well, maybe there's some value in red wine. I'd say drink a glass of red wine a day, and it improves health. But there's an alternate possibility here, right? Maybe it's just that healthy people prefer to drink red wine. But also just because there's a relationship between variables, it doesn't mean that a third unexpected variable might be influencing your results, right? And this is something that's potentially problematic with correlational studies, right? Is that the correlation could be described or could be really being caused, right? This is sort of why inferring causality is tough. The correlation could be caused by a third variable, right? Maybe it just comes down to people with enough money to drink red wine, because red wine can be typically expensive, particularly if you like any good. I'm not talking about the $5 bottle Trader Joe's. Don't be absurd. I'm talking about actually good red wine, which is, if you're going to drink it, you may as well be good, right? And so maybe people with enough money to drink red wine, they can afford a healthy lifestyle in general. I don't mean to bag on cheap Trader Joe's red wine. I'll use it if I'm making sangria. There's no sense in wasting a good bottle of red wine if you're just going to mix it with fruit and brandy and sugar and orange juice. But if you're going to, pro tip to the youngsters out there, any wine worth drinking should be good. That won't be on the test, though. All right. Now, another way of doing research in psychology, right, is to do a proper experiment, right? So in this case, the researcher's manipulating at least one variable and looking for changes in another variable. And so what we're manipulating here is something called the independent variable, right? It's a variable that is manipulated by the researcher. And then what we're measuring, right, what the output is what we call the dependent variable. And this is a variable that's observed to assess the effects of the independent variable. So maybe I assign a new class project to see if it improves students' understanding of the material, right? And maybe I have one group that does it the old way, and I have a new group that does it the new way. That's what I'm manipulating, right? The old way or the new way is the sort of independent variable, right? The class project is the independent variable. And I have two levels of that: the old way that I taught the class, and the new, the old class project and the new class project. And I have one group do one group do the other, and then I see if they're maybe in some sort of test, right? Whether or not their understanding of the material has improved. And the output of that test, in this case, is the dependent variable. One way that you probably might seem obvious to you guys, you probably heard about this before you ever took this class, is how do they do drug testing? Well, typically, if a drug is approved by the FDA and ready for human testing, then they probably have a group of people called placebo, right? That means that they receive the drug, but it doesn't have any of the active ingredient, right? There's nothing in it. Typically, it's a pill that has none of the chemicals that might be used to treat the symptoms. And then another group might have the pill, but with the active ingredient, right? That's the independent variable here, the type of pill they get, right? And then they check after a certain period of time of taking either the drug or the placebo to see if it reduces symptoms associated with a particular illness. So that would, the reduction of symptoms, whatever output that is, right? They could tabulate that, count that in some way, measure that in some way, and that would be the dependent variable. So the big point here with an experiment is rather than just measuring two variables as they sort of naturally occur, which we might do with correlational research, the researcher is manipulating a variable and also tries to exert some sort of control over the research setting and the participants. to make sure that any sort of extraneous thing, any sort of extraneous variables other than the independent variable aren't what's impacting the dependent variable. Let's go through a few examples here. I think these are good examples here because, first of all, they're very similar to what I'm asking you to do on question 1 of your first homework assignment. But also, you could typically expect questions like this on the exam, a handful of them, where I'm going to ask you to do things like read a scenario and be able to explicitly identify the independent variable and the dependent variable. And in later exams and homework assignments, you're also going to be asked to identify these specific statistical tests that you might need to employ in order to perform the analyses. And so I'll read these through. You can go ahead and pause the video, think about what your answer might be, and then unpause the video and I'll give you the answer. So here's one. Do customers spend more money if they're greeted as they enter the store? So maybe in week 1, you've got an employee that greets all the customers as they enter the store. And in week 2, there's no greeter. And the average amount of money spent during week 1 is compared to the average amount of money spent during week 2. Does the presence of a greeter impact sales? Go ahead and pause the video and see if you can come up with an answer. So the independent variable here, what's being manipulated in this case is whether or not there's a greeter, right? Presence of greeter or no greeter. So that's the manipulation. And the dependent variable, what they're measuring as an outcome or an output, is the amount of money spent. Let's do another. We'll do 3 in total. Who makes a better cake, me or Brendan? So 15 of our friends and family sample cake A and cake B. They rate each sample on a scale of 1, yuck, to 10, unbelievably delicious. So pause the video, think about what the independent variable is, think about what the dependent variable is. So the independent variable is the type of cake, right? Either cake A or cake B. That's what's being sort of quote-unquote manipulated in this example. And the dependent variable, what our output is, what we're measuring, is the taste rating, right, on a scale of 1 to 10. Let's do one more. This is a harder one, but this is a little bit more experimental, I think. Participants in a research study are asked to memorize a list of words and then perform a series of math problems. For 1/3 of the participants, the list is easy with short, related words. For another 1/3 of the list is very hard with long, or for another 1/3, the list is very hard with long, complex words. And for the final 1/3, there is no list at all. Is the number of errors that a participant makes on the math problems impacted by the difficulty of the memory task? And before you pause, let me just point a few things. I like questions like these a lot because some of this has nothing to do with what you're trying to answer, right? It's a good example, a somewhat decent example of an experiment in psychology. But the point is there's a lot of information that isn't necessarily relevant to the question I'm asking here. So you've got to do a little bit more thinking and sort of you're reading a little closely to make sure you get the correct answer. So go ahead and pause the video, see if you can determine what the IV and the DV are. So the independent variable is the word lists, right? A third of the class, or 1/3 of the group gets easy, 1/3 of the group gets hard, and 1/3 of the group gets no list at all. Right? So that's what's being manipulated. The difficulty and or sort of even presence of a word list. And then the dependent variable here is the number of errors on the math test, right? So we're doing a memory test, right? It's manipulated in 3 different distinct levels. We're measuring sort of the impact on whether or not the memory task makes math problems more difficult. So our output here, what we're measuring ultimately, is the number of math errors. So let's talk a little bit about this idea of an experimental condition versus a control condition, because there was a control condition in that last example, and that was the group that just simply did the math problems and didn't participate in the memory manipulation, right? And so they can be treated as a baseline in which you can compare your experimental condition or conditions against that baseline. And so typically in an experimental design, we're trying to exert a high degree of control over the experiment by comparing the group that experiences the manipulation with the group that doesn't experience the manipulation. And this means having an experimental group or groups and a control group. And so individuals in the control group, they don't receive the experimental treatment. They serve as a baseline group, right? Right. So that's really sort of all there is to say about that. The last slide. See if I can put my cursor up. This group that didn't receive the list at all, well, that would be a good control, right? Because the manipulation, since they don't experience the manipulation, then then the memory test shouldn't have an effect on their math problems because they didn't do the memory test, right? So this can be sort of a baseline group that the other two groups that have experienced the manipulation can be then easily compared to. But the point is, when we do things like exert control or have control groups rather, when we try and make sure that extraneous variables aren't affecting our results, then a well-designed experiment allows us to make cause and effect statements because we're doing a better job. We're trying to make sure that the best we can that extraneous variables aren't influencing our data. Or if anybody has extraneous variables, ideally, we'd like to, because they probably do, ideally we want to make sure that any groups that we create out of a larger group, that those extraneous variables that people might have are sort of equally represented in all three groups, right? So ideally, you would want to make sure, depending upon what your study is interested in measuring, that, if you create multiple groups, like we did in that previous example of the memory test, well, you want to make sure as reasonably as possible that everybody in all three of your groups roughly has the same intelligence, right? That variability of intelligence that we have in a population is reflected in your groups, right? And so we do this by making sure that we randomly assign all of our participants into the experimental group and the control group. And the idea is this will balance out extraneous variables and it will help eliminate confounds, right? So, here's a question so often asked in psychology. Does playing violent video games increase people's aggressive behavior and subsequent interactions with others? And you could have an experiment where you have some participants play a violent video game, and then you have others play a non-violent video game. And after they play the game for, say, 20 minutes or so, you put them in a social situation, and you observe how aggressive they are. Now, if participants who played the violent video game behave more aggressively than participants who played the non-violent video game, you might be able to say that the violent video game caused people to behave more aggressively. Like, ideally, that's sort of how we want to do science, right? But we can think a bit more critically of this design, and it's worth it to always do that. What might be something that we wonder about the participants before we perform the experiment? Like, for example, we might be interested in how aggressive they are to start with, right? We might be interested in how often they play video games. Right? These are characteristics that vary from person to person. They might not necessarily be of interest to us in a particular study, but they're variables that might have an impact on our dependent variable, even though we're not necessarily concerned with, say, studying them at this particular point in time. So the fact of the matter is everybody that's going to be in your study, they're going to have sort of different levels of natural aggression, right? Some people, just by the luck of the draw, right? You know this just by meeting people. Some people are going to be not very aggressive. Some people are going to be extremely aggressive. Most of us are probably somewhere in the middle, right? Maybe situationally aggressive, right? There's also going to be variability in the amount of time that people spend playing video games, right? Some might play very, very little. Some might play all the time. Some might be a little bit more casual. Who knows what that distribution looks like, but we do know that it's not the same for everybody, right? So the fact that these sort of characteristics vary, and so before I sort of say that, you would want to make sure, right, that you weren't putting, you want to note the effect of a violent video game has on social interactions. But what would happen to your data, for example, if somehow the people that ended up in the group that played the violent video game, they all just happen to be extremely aggressive people, right? It has nothing to do with a video game. They're just aggressive people, right? Because we know that happens. Well, that might adversely affect your results, right? You might find a lot of aggressive interactions that have nothing to do with playing the video game. It might be that that's just their typical behavior, right? So the idea is that but you're going to have some people that are aggressive. So you want to make sure that the people in both your, sorry, let me take a sip of coffee. All right, let me back up. We know that some people, we know that you might have a handful of people that are not very aggressive, and a small group of people that are very aggressive, and again, maybe sort of the bulk of people are situationally aggressive, right? And this creates sort of a nice, sort of even distribution, like a bell curve, if you will, of sort of typical aggressive behavior in human beings, right? You want to make sure that in your two groups, right, your group of that's playing the violent video game and your group that's playing the non-violent video game, that same sort of distribution of aggressive behavior, right, that you find in the population is reflected in both groups in as even a way as possible. So in other words, if you have people in the population where you have a handful of people that aren't very aggressive at all, and a lot of people that are, but most people sort of in the middle, then you want that same distribution of aggressive behavior to be in your violent video game group and your non-violent video game group. This way, right, that's controlled for, that characteristic is controlled for, is equally represented in both groups, right? So as a consequence, if it ends up that people that play the violent video game are more aggressive than people that play the non-violent video game and their subsequent interactions that you're measuring, it's not because you ended up with a bunch of people who were more aggressive than not in your violent video game group, right? It's because of the manipulation, because you've taken steps to control that both groups have the same sort of aggressive aggression characteristics prior to the start of your study. The way you deal with this, the way you make that happen, is by randomly assigning people to groups, right? So the point is, using random assignment, each participant has an equal chance of being placed either into the experimental group or into the control group, right? So random assignment doesn't eliminate the fact that people differ on certain dimensions. Its goal is simply to distribute those differences as evenly as possible among the groups. So, if there's a difference in intelligence, or in this case, what we're talking about with this example, aggression, that can impact the dependent variable, random assignment ideally will help. There's never a 100% guarantee on this, but it will help to ensure that this is balanced out. And this helps us protect from something that we call a confounding variable. It's a variable that you don't account for. Well, it can help protect, but also confound can be completely unrelated. It can be something you just didn't expect. But it's a variable that you don't account for that ends up having an unforeseen effect on the dependent variable. And we talked about this with the wine and health example, one of the earlier slides. Basically, it means that something other than your manipulation, right, of the independent variables is affecting your dependent variable. Here's I think, a good example. Let's say I want to know how different types of music affect relaxation. And maybe I have people listen to classical music, then country music, and rock music for 20 minutes. And I can measure the level of relaxation. So here my independent variable is going to be the type of music they listen to, right? Because one group's listening to classical, one group's listening to country, and one group's listening to rock. So that's what I'm manipulating, is the type of music. And my dependent variable is going to be some sort of metric of relaxation, right? On a scale of 1 to 10, how relaxed are you? But I think about this and I say, well, I want to make this experiment more realistic, right? So what I'm going to do now is I'm going to play the classical music to that group at a low volume. I'm going to play the country music at sort of a moderate volume. I'm going to play the rock music at a real high volume. And then I do the study again. And what I find is the group that listened to the classical music was the more relaxed group, particularly compared to, say, maybe the rock music group, which was the least relaxed. Well, I've introduced a potential confound here, and having these volumes of music different here, right? I don't know, it could have been that the low volume, not necessarily the music itself, but the low volume of the music, that might be what's more soothing. It might not necessarily be because it's classical music, right? The fact that I pumped up the rock music at some crazy volume, well, maybe that's what's leading to sort of higher stress scores, right? So I can control this problem by holding things like the volume of all the music, regardless of the condition, constant, right? So that's not something that might be influencing my measure of relaxation. The last research methods thing I want to talk about here is this idea of a quasi-independent variable. So it's a pre-existing variable that we might use to create two groups, right? So in this case, we can't use random assignment. And when you take research methods, you'll see this referred to as not a true experiment, but they're called a quasi-experiment or whatever. But understand it's still experimentally rigorous, right? People have to do these studies all the time, and you'll see why in a second. And importantly, I want to point out that the procedure and the logic for running a quasi-experiment like this are all very similar to a typical experiment. We also use typically the same terms like independent variable and dependent variable. Now, why would we run a quasi-experiment, right? Why would we have a quasi-independent variable? Well, it could be because it's impossible, or maybe it's unethical to do random assignment. Here's the best example, right? Let's say I'm interested in the impacts of health impacts of smoking. Well, I can't assign a non-smoker to a smoking group, can I? I can't, run a study, and if you're a non-smoker and you come in to participate in my study, well, in order to be in this study, you have to start smoking 2 packs of cigarettes a day, right? Like, we can't do that. It's unethical. So you rely on people that self-identify as a smoker or a non-smoker, and then you put them in their respective group that reflects that characteristic, right? And then you can measure the health effects for that. So, there's some things that we just can't do. Maybe I'm interested in studying learning outcomes, but it depends on your class in school, right? Freshman, sophomore, junior, senior. Typically you're one of those 4, right? I know there's some. You could be a post-bac, or you could be sort of. There's kind of a little in-between sort of thing, but typically, as you go through college, you're one of those 4 years, and that's a fixed variable in that case. I can't manipulate that. If you're a freshman, if it's your first day of school, you walk into my study. I can't make you a sophomore. I can't make you a junior or senior. So if I'm interested in sort of some outcome performance based off your year in school, I can't manipulate that. I have to put you in that appropriate group, right? So I can still run a very good experiment. I can control for confounds. I could do good manipulations. I can do good measures, and it's still real quality science. But there's something that's sort of restricting us in this sort of quasi-experimental design from doing any sort of random assignment, because maybe we're specifically interested in that particular pre-existing sort of variable. All right, so let's get a little bit more in the weeds here on some more terms that really sort of define how we measure variables. So an operational definition, it defines exactly how a variable will be measured, right? It explains how we can translate a variable into something that we can measure. And this is, always a big challenge in science, particularly in psychology and neuroscience, because we might say, well, here's this example on the slide. Maybe we're interested in measuring college success. Well, that's fine, but on its surface, that's very difficult to sort of pin down, isn't it? Because college success may mean something different for just about anybody you ask. But within an experiment, our goal, right, is to sort of pin down a reasonable definition of that. And we have a lot of latitude here in how we choose to define that, right? But it should be reasonable, and people can have different opinions on it, but it should be something that go, yeah, that's a reasonable metric of college success. So maybe GPA at time of graduation might be a good indicator of college success. Maybe some people would disagree, again, but other people go, yeah, that seems reasonable, right? If you've got a high GPA when you graduate, then one could argue you've done well in college. We could make this a more binary choice, right? We could say, well, we could make it a yes or no sort of thing. Like, did you graduate, right? If you mark yes, well, then that's a measure of college success. But if you say no, right, then well, that isn't. We can ask the same thing maybe about job placement. Were you able to get a job in the field that you were interested in after college? It's sort of a yes or no as well. Some people even think salary, right? Maybe I think that's also actually a big thing that's in the news, that people are looking at salary, not immediately, but like 10 years out, using that as sort of a metric of whether or not it was worth it to go to college. But the point is that there are a lot of sort of things we're interested in measuring that, when we just say them, right? You'll hear these referred to as constructs when you get into research methods. We just say what they are. They're a bit nebulous, right? Like, I want to measure aggression. Well, what is that, right? Like, you might be familiar from your intro psychology class about the Bandura study, right? Where they were measuring the effects of vicarious learning of aggression, right, through the Bobo doll. Well, that's a great job, right? That's a way of pinning down that metric of aggression that you want to measure. But if you just say, I measure aggression, or I want to study aggression, well, you need to operationally define it. Intelligence, that's another good one. Like, intelligence might mean a lot of things to a lot of people. If I want to measure intelligence, maybe that's sort of broadly what I'm interested in. But maybe I'm measuring memory on a specific test that I devise that happens in the lab. So I say I'm interested in studying intelligence, but I have to operationally define what it is exactly that I'm measuring when I do an experiment. So those things are all variables that, in that they're characteristics that can take on different values or levels from person to person, but these variable names alone don't explain exactly how we're going to measure that particular concept. Variables also can be, when we talk about how we measure a variable, typically the output is either discrete or continuous. In discrete variables, these are variables, these are the easiest sort of ones to wrap your head around. They're variables in data that is consistent, that consist of separate indivisible categories. So what does this mean? It means that no values can exist between neighboring categories. Some examples. Maybe one's marital status, right? I mean, you're either single, married, divorced, widowed, right? I mean, you're one of those things. You can't be married and single simultaneously, right? I'm not trying to be sort of cheeky here, but it's an indivisible category. How about the number of TVs that you might have, if anybody has TVs anymore? You don't have 1.3 TVs, right? You have one TV, or you have two TVs, or three TVs, but you don't have some fractal amount of TVs. A TV is a indivisible thing, right? Children, right? How many children does somebody have? A person has one child, or two children, or three children, but they don't have 2.7 children, right? A child is not a divisible thing. Number of students in this class, right? That's something that is indivisible. All of those are examples of discrete variables. If you cannot fraction them, right, then it is a discrete variable. A continuous variable, on the other hand, has an infinite number of possible values that can fall, this is the key thing, that can fall between any two observed values. So it's divisible into a seemingly infinite level of fractal parts, right? Here I have sort of a measurement scale up here, right? We can pretend this is distance or weight or something like that, right? With any continuous value of data, the scores have real limits, right? The points that fall half a measurement unit below and above the number, right? So in this measurement situation, like let's say we're talking about an observed value of 151. Now that value would be obtained, right, if the real value were 100 and somewhere over here, like 150.8 or 151.2, or any value really between 150.5 and 151.5. So the observed value of 151 actually represents the real values from 150.5 to 151.5. And these values are called real limits. If it seems confusing, don't worry about it too much, because we're going to talk about it again very briefly later on, right? Typically when researchers are working with data, the concept of real limits isn't something that we would typically talk about, but it's something you need to be aware of for now, because it relates to the way we're going to talk about variability when we start talking about ranges of values of a data set. And We're going to get to that when we get to chapter 4. You also need to understand the 4 types of data that we'll be using this semester: nominal, ordinal, interval, and ratio data. Nominal data is discrete data, right? So it's going to be data that we talk about in whole values, right? It's indivisible. So again, the number of children would be nominal data, number of TV sets you own, so on and so forth, right? It's indivisible, right? Note here this little example. I should have a question mark there. Let's say, imagine you're asked, what's your favorite type of music, right? You select, you're only given one of these 3. You select one of those 3. You're selecting a category, right? But here we can associate a number with it. We can do that sort of arbitrarily as researchers because it typically makes it easier to code. But the point is that we'll have a certain number of people that select 1, a certain number of people select 2, a certain number of people select 3. But we wouldn't be able to do any meaningful math with those numbers, right? So in other words, you couldn't use these generic numeric designations to do things like computer mean. It is traditional, however, to count the number of occurrences of a nominal variable. So, if you were all asked what your favorite type is, you give an answer, and if we tabulated that up for the class, we could get a count of how many people preferred one of these 3 types of music. And one way to remember nominal data, make a sort of connection, is it sounds like name, right? So it means a category. It means categories of discrete data. Then ordinal data, that's the second one. These are quantities that have a natural ordering. I can't read my slides today. And what's some examples? Ranking of favorite sports, right? You can rank, my favorite sport is soccer. My second favorite sport is baseball. My third favorite sport, blah, blah, blah. Note that it's different here. This is just saying, okay, what's your favorite type? You get to pick one, right? Here in ordinal, you're being asked to rank something, right? People's place in line, right? The person in front of me is first, I'm second, person behind me is third in line, fourth in line, so on and so forth. Another good one is the order of runners finishing a race, right? So this person finishes first, this person finishes second, third, so on. And importantly, with ordinal data, we don't know the distance between each interval or whether the distance between any 2 particular values are equal. So let's say you have somebody running a race, they finish in first place, they finish the race in 2 hours and 32 minutes. Well, then you have a person finishing second place. They finish 2 hours, 47 minutes, so they're 15 minutes slower, right? There's a 15-minute difference between first and second. And the person that finished third finished the race in 2 hours, 50 minutes, so they were 2 minutes slower. So we know that, okay, somebody finished first, somebody finished second, somebody finished third, but this sort of ordinal data doesn't tell you anything about how big the interval was between them, right? So we don't know the distance between whether or not those the distance between any finishing place or ranking place is equal, right, between the 2 points. And so we often use rating scales in psychology, right? We call them Likert questions. And so on a 10-point scale, maybe the difference between a 9 and a 10 isn't necessarily the same difference as the difference between, say, a 6 and a 7. And one way to remember sort of ordinal is that it sounds like order, right? Putting things in order. Then we have interval data. So this is like ordinal data, except that we can actually now say that the intervals between each value are equally split. So a good example is temperature in degrees Fahrenheit. So the difference between 29 and 30 degrees is the same magnitude as the difference between 78 and 79. With attitudinal scales and the Likert questions you usually see in a survey, these are rarely interval for the reasons that I explained in the last slide. But although many points on the scale likely are of equal intervals. And another important thing here is that it might have a 0 value, right? Like degrees in Fahrenheit. But that 0 is just yet another measurement. It doesn't mean the absence of the variable, right? And that's an important distinction to make, particularly when we talk about ratio data, because ratio data is like interval data, but it has a natural absolute 0 point. So what's examples of ratio data? Time, right? Because if you were running a race and we wanted to measure the time it took you to run, say, a 40-yard dash, well, we're at 0 before we click the stopwatch or before you start, right? So that means an absence of the measurement, right? Degrees Kelvin has a 0 point, right? An absolute 0. And the steps in both those scales have the same degree of magnitude, right? There's the same degree of magnitude between differences. Weight is a good one, right? If something weighs 0 pounds, it has no weight. So 0 indicates, in the case of ratio data, an absence of the variable. But think about it in terms of interval ratio. If it was 0 degrees outside, it doesn't mean that there's an absence of weather, right? 0 is just an arbitrary another point in the measurement, right? So that's the important distinction to make between the two. So here's some examples, right? We might ask, are you currently in pain, right? And the answer to this is a nominal variable, because you're either saying yes or no. Another good example of nominal scale would be, how do you characterize the type of pain? Is it sharp, dull, or throbbing? So you're giving a nominal response, right? A categorical response to the type of pain you're experiencing. Compared with yesterday, is the pain less severe, about the same, or more severe? So now we're ranking our pain in an order. Now you might look at the bottom one and go, oh, well, there's a pain scale here, right? From no pain to excruciating pain. Isn't this ordinal as well? No, it's ratio, right? Why ratio? Because it starts at a real 0, right? And that 0 is no pain, right? So you can't have sort of a negative value for that pain. So there's only one place to start, and that's 0, and that 0 indicates an absence of that particular variable. Here's some other ones, right? Your age, right? Well, this would be ratio data, right? Because you can't be anything less than 0, and a 0 age indicates an absence of existence, right? You're not born, right? The person doesn't exist. So that 0 is a meaningful number. But we can also ask for age in a different way, right? We can bin them in different ranges, starting at one value, going to a highest value. And now we're binning these ranges in an order, so that would make them ordinal data. Golf score, right? So here I'm not talking about par. I'm talking about the number of strokes, either by hitting the ball through the course round of playing 18 holes, or penalty strokes that might be applied if you make a mistake. That's ratio data, right? Because you start off at 0. In par you might have a negative score, but I'm talking about your golf score based off the accumulated number of strokes for the day. So it's going to start off at 0 and work its way to, if you're like me, 120. How about annual income from all sources? Well, this would be an example of ratio data as well, right? We sort of start off with 0, making $0 a year, and hopefully go up to something quite high. Being in debt notwithstanding, there's typically, you don't make negative money a year. I mean, you say, oh, you lose money in a business, but sort of describing this in the real world, like, if somebody says, well, what's your annual salary? You would say, it's negative $20,000. Like, no, it's somewhere between 0 and typically some other number. In E here, this is an example of nominal data, right? The type of government, right? A unitary, federal, or a confederation. And these are all, distinct, indivisible categories. So this is nominal data. And last one here, this is also an example of ordinal data, right? This is data from 2010. These were the top 10 programs with product placement activity. And so these are all ranked in order from 1 to 10, right? So American Idol had the largest example of product placement, whereas Undercover Boss had the lowest. So, the last thing I'll say about measurement scales is they can influence the kind of statistics that we can and cannot use, right? So certain statistical procedures require certain types of measurement scales. So statistical tests, they're performed on numbers, right? They're performed on value data. And that data doesn't remember where it came from, right? That's up to the researcher. So you can perform any statistical test that you want on any data set. But your interpretation is only going to be meaningful if you've used the acceptable test for the measurement scale that you're dealing with. So it's an important thing as a researcher, data analyst, to understand what type of data that you have before you start. Is it nominal, ordinal, interval, ratio? So that you can select the correct test to use. And I should say that, on exam, you'll need to be able to identify the measurement skill. In fact, there's several questions, or not several, but there's, I want to say it's probably question 2 where you're asked to do this on the homework, right? So this is something that you'll need to know on the homework as well as the exam. All right, and so we're going to finish up here with a little bit of mathematics here, right? In fact, question 3 on homework 1 deals with statistical notation or mathematical notation. And it's pretty important that you understand this. We're going to do a few problems here together, but I want to explain a little bit about the statistical notation that you're going to need to know. A couple of sort of examples. So if you see, this is now we're moving into doing math with a lot of letters in it, but it's not as hard as it sounds. But this is an important thing to understand because we're going to do this for the entire semester. So if you're given some sort of mathematical formula in this class, you see x, right? X. That means all the individual scores obtained from a participant. But you might see x and y pairs, right? You might see an x and a y if multiple measurements are used. And that x and y pair represents 2 observations from a single participant, an x observation and a y observation. You also see things like n, right? Big N, uppercase N. In that case, we're talking about the entire size of the population. If you see a lowercase n in a math problem, that means we're just talking about the size of the sample. And finally, you're going to see something that maybe this might be the first time you've ever seen it. It is the uppercase version of the Greek letter sigma, and that means the sum of. So if you were to see something like sigma x, right, like what you see right here at the bottom, sigma x, that would be telling you to sum up all of the individual scores, obtained from all your participants. So sigma x would be add up all the scores. It's also worth talking about here this idea of order of operations, right? You might have learned this in math, right? There is an order with which you solve different clauses of a long equation or math problem. And first and foremost, you want to solve anything that's in parentheses. So I've got a little crazy sort of example right here. But if we were to do this math problem, we see we have 2 terms in parentheses, right? So we'd want to do those first. Then before we continue on, we'd solve anything that has exponents in it, right? So that would be next here. Note, this has exponents, but we would solve that in the process of dealing with this parenthetical term, right? So we're assuming we've done this and done this. Now the next step is we ask, is there any exponents in the problem? Oh, indeed there is, so we need to do this. Then we would do anything that's multiplication or division. In this case, we don't have that in this problem. Then we would do summation using sigma, but that's not going to apply here. I'll discuss that on the next slide. Then the next thing we do is addition. Well, we would add whatever this value was with this value, right? We wouldn't subtract first, we'd add, and then we do the subtraction, right? So we'd get some term for this, and we would and then subtract it from that. So I'll try and use my little stylus pen for my Surface Pro. So if we were doing 4 squared plus 3 times 2 minus 2 squared plus 3, we might, let me try and do it as such and see if this works. 4 squared plus 3 times 2 minus 2 squared plus 3. All right, so let's do this first term, right? 3 times, because we have to solve the parentheses first. So 3 times 2, right, is 6. So we can write 6 under here. And then let's do this term. 2 squared is 4, plus 3 is going to give us 7, right? So now we need to do anything with exponents. Well, 4 squared, right, 4 times 4, that's 16. Oops, come on. Thought my pen died, right? And so now we don't have any division, right? We don't have any, we don't have any multiplication. We don't have any division. We're not summing anything doing sigma, but our next step is to do the addition, right? So we're going to do, so what we're left here is when we solve these little terms, come on, is 16 plus 6 minus 7. So we need to do this first. So 16 plus 6, right? It's going to give us 22 minus 7, right? It's going to give us 15. Okay, so that's how you would do the order of operations for somewhat complex problem like so. But now let's introduce sigma, right? The idea of sigma is that we're going to sum up things at certain steps, right? So if you take this, we can do all of these together here. If you take sigma x, we mentioned this on a couple of slides ago, sigma x means to sum up all of your values of x. So if we were going to do sigma x, right, then we would simply add 1 plus 2 plus 3, right? And that equals 6. What about sigma x squared, right? Well, remember your order of operations. We can't just take 6 and square it because exponents comes before addition. So what this is telling us, what sigma x squared means, is that we need to square each x value first, right? Because let me go back to the previous slide. Note that exponents comes before sigma, right? So we need to do that first. We need to square each one of these values and then sum them up. So we go 1 squared plus 2 squared plus 3 squared. And so what do you get? You get 1 plus 4 plus 9, right? And so you're going to get 14, right? Because 1 squared is 1, 2 squared is 4, 3 squared is 9. When you add all that up, you get 14. What about the next one? We have sigma with x minus 1 in parentheses. So again, let's go back to our previous slide. Again, note that parentheses comes before sigma. So we need to do whatever is in that parentheses term, and then we can sum them all up. So this is telling us to take each x value, subtract 1 from it, and then add them up. So what you're going to be basically doing is going 1 minus 1 oops, plus 2 minus 1 plus 3 minus 1. And we don't need to break this down. Like 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 1 is 2. So the answer to this is 3. Hopefully you can see this fairly well. I'm just bought this Surface Pro, so I'm still trying to learn how to write with it a little bit more clearly. Let's move to the next one. It says sum of x minus 1. So again, let's go back to our order of operations. What we've got here is a sigma problem. So, sorry, let me go back. Sum of x minus 1. So remember our order of operations. We've got sigma x and we've got a subtraction problem. So if we go back, we see that summation using sigma comes before subtraction, right? So what this is telling us to do is to find the sum of x, which is happened to done already up here, and just subtract 1 from that. So the way to do this is it's 6 minus 1 equals 5, right? And then finally, we have this last one here, sigma xy. Well, maybe you recall, if you learned this before in school, that when two variables aren't separated by an operator, well, that means multiplication, right? So this means sigma, so this means x times y. Sigma xy is basically asking us, remember, so multiplication comes before summation using sigma. So what this is telling us is that we need to multiply each x and y pair, right? 1 times 5, 2 times 10, 3 times 15, and add them up, right? So if we were to go, 1 times 5 is 5, 2 times 10 is 20, 3 times 10 is 45, right? 1 times 5 is 5, 2 times 10 is 20, 3 times 15 is 45, and then saying add these up, right? So we're going to get 0, because that's 10. 5 plus 5 is 10. We carry that, and we're going to get 70. Great. So, this can be a little challenging, right? If math isn't your strong suit, my advice would be to go to the appendix in the back of the textbook, and I think it does a pretty good job of helping you out with these as a bit of a refresher. But math is part of this course, and is in all of the assignments you always want to show your work, because I'll give partial credit if I see you're on the wrong track, but maybe you've got the wrong answer because you just made a slight mistake, because it happens. But if you don't show your work and you get the wrong answer, then you're going to get the whole thing wrong, right? So, but anyway, there is math in this course, a lot of math in this course. And some of it may seem daunting, but I'll do the best I can to show you how all these things sort of break up into, a series of steps. All right, so that's it for the day. That's it for this lecture. You should be able now to answer questions 1 through 3 on the homework, and remember to check the site regularly for things like quizzes and lecture slides, right? But all of that is covered in the syllabus. So that is it. I am done for today. So